we're given a problem where we have an open box with a square base that has a volume of 4 cubic feet. We want to minimize the surface area. If this has a square base, that means we could say that this side is x, and so is this one. And then we have a height, we'll call y. That's different from those two sides. This is like the one we did in notes today. We want to find the equation for the surface area if that's what we're trying to minimize. So we're minimizing the surface area. Well, we have 4 sides around the box, and those are all going to be the same. They all have an area of xy. So we have 4 times x times y, which is the area of the 4 sides surrounding the box, plus the area of the base, which is x squared. But just like in the notes today, we can't have 2 variables in this equation on the right side. We need to substitute something in for y. So that's where the volume comes in. For this, volume, length times width times height. So in this case, our volume is 4. Length and width are both x, and our height is y. So y equals 4 divided by x squared, or 4 times x to the negative second. So we can substitute that in place of y into our surface area equation. So 4x times 4x to the negative second plus x squared. A little simplification here, we get 16 times x to the negative 1, because when we multiply these two, we add their exponents. We get x to the negative first plus x squared. Now that we have that in terms of one variable on the right side, we can take the derivative of the surface area. And we get negative 16 times x to the negative second plus 2x. So now we can factor out 2x to the negative second. We get negative 8 plus x cubed, because x to the first divided by x to the negative second. We subtract those exponents, we get x cubed. So we can write this as 2 times negative 8 plus x cubed all over x squared. And we want to know the critical values, which are when the derivative is 0 or derivative is undefined. But just like before, if we set this denominator equal to 0, then we're going to get something that's 0 for length or width. That doesn't make any sense for this problem. That doesn't work. So we do want to find the critical value where the derivative is 0. So we can set the numerator equal to 0. If we divide both sides by 2, we get negative 8 plus x cubed equals 0. Add 8 to both sides. Take the cube root. X equals 2. So our derivative of s of x is equal to 0 when x is 2. If we put something in less than 2, like 1, negative 8 plus 1 cubed, that's going to give us a negative number on top. 1 squared on the bottom is positive, so we're going to get a negative derivative to the left. And if we put a number bigger than 2, like 3 in here, we're going to get a positive over a positive. Which tells us that the graph is decreasing, then increasing. So at this point, we do have a minimum. So we have a minimum at x equals 2. So that's, the width is going to be 2 feet. The length is 2 feet. And then to find y, we can substitute into either one of these equations. This one makes a little more sense. Y equals 4 over 2 squared. So that gives us a height of 1 foot. That minimizes the surface area in this problem.